this video, we will discuss the problem number of occurrences. Previously, this problem has been asked in companies like Amazon. So let's read the problem statement. Problem says that we'll be given a sorted array and will be given a number that is a target number. And you need to find the number of occurrences of the target in the array. So let's take the first test case here. If you will see the first test case, so we have been given the array as 1 1 2 2 2 2 and 3. So we have been given this array. Now the target element is basically 2. So we have to find out how many times 2 is occurring. So 2 is basically occurring 4 times in this sorted array. So the answer would be 4. Now if you see the next test case, in the next test case the target element is 4 and 4 is not occurring in this array at all. So the answer is basically 0. If you see the last test case here, so the target is 12 and 12 is occurring 3 times. So the answer for this is basically 3 here. Now how can we solve this question? So let's discuss the approaches for solving this problem. So the first brute force approach would be that we can basically iterate throughout the array using linear search, and we can check each and every element of the array. If it is equal to the target, then we can increase the counter variable, and this would take order of n time because we'll be traversing throughout the array and the space complexity would be order of 1. Because what we will do is we'll make a resultant variable here, and then after that we'll start iterating throughout the array. If the ith element is equal to the target, then we'll increase the counter, and then at the end we'll return this resultant variable which is indicating the counter basically. Let's take one sample example. Suppose if we had the array that was 1, then we had 2, then we had 2, then we had 2, and then we had something like, let's say 4 here. Suppose my target element was equal to 2 here. Now what will happen in this linear search approach is, initially my result variable will be 0. I'll iterate and check every element. So firstly this element is not 2, next element is 2, so increase the result, it will become 1. Another element is equal to target, next element is also 2, so increase the result. Now you go to the next element, it is also 2, so increase the result, it will become 3. So this means target element has appeared 3 times so far. Then you go to the next element, it is not equal to the target, so the result still remains 3. Then we reach the end of the array, finally the result is 3, which is a linear search approach. But this approach is taking order of n time because you can observe that we are iterating throughout the array. So this will take order of n time here. And the space complexity for this approach is order of 1. Can we optimize this a bit more? Yes. Since the array has been given as sorted, so we can use the property of sorted array. So we can apply binary search here. Now in terms of the application of binary search, it is not like we have to directly apply the basic binary search algorithm. We'll be applying the modifications or the applications of binary search, that is the lower bound and the upper bound concept for solving this problem. We'll understand this through the dry run of the sample test case as well. So if you see here, since the array is already sorted, so we can use binary search to find the occurrence of the given target. Now there are two concepts that we are using. First is the lower bound and second is the upper bound concept. Now lower bound concept does what? If the element is present in the array, then lower bound concept will give me or will find or will search the first occurrence of the element of the target element in the sorted array, and upper bound will do what? Upper bound will find the first element or the index of the first element that is greater than the given target element. Okay, and the differences between the two index will be the total number of occurrences. How? So basically if you will see this particular given array, so what will happen is if you do indexing here 0 1 then 2 then 3 4 5 6 7 8 9. So since we know that lower bound will always indicate the very first occurrence, index of the very first occurrence of the target. So lower bound will be equal to what here? Lower bound will be equal to 1 here. And the upper bound indicates what? Upper bound indicates the index, or upper bound will stand at the index of the very first element that is greater than the target. So upper bound will be standing where? Upper bound will be standing at this particular index, which is nothing but 5, because the very first element that is greater than 2 is basically 3. So the upper bound will basically stand at the element that is nothing but 3 here. So the upper bound will be at the index 5. It will be at this element 3. Now what will happen is, what is the difference between the two indexes? If you do upper bound index minus the lower bound index, what will you get? So you will basically get nothing but 4, because 5 minus 1 is 4, and the number of times the element 2 is occurring in the sorted array is basically 4 here. So this is how the lower bound and upper bound concept will help me to reach the final answer. But we need to discuss the basic intuition of lower bound and upper bound first, and then we'll see the dry run that how we can modify the basic binary searches to implement lower and upper bound. If you will see here, firstly, lower bound is what? Lower bound will give us the index of the first occurrence of the target element. If the target element is present, then it will give us the first, it will give us the index of the first occurrence of the target element. If suppose sometimes the target element might not be present in the array, then it gives what? Then it gives the very first position where we need to insert the element to maintain the sorted order. So this is one unique thing about lower bound, that if the element is not present, then it will give the very first index or the index where we should insert the target element so that we can maintain the sorted order. The upper bound does what? Upper bound will basically give us the index of the first element that is greater than the given target element. Now let's see this using the sample test case here. Suppose that this is the sample test case that we have. Now let's do some indexing here as well. So index 0, index 1, index 2, index 3, index 4, index 5, 6, 7, 8 and 9. Now if you see here, initially what we will do is we'll update the lower bound value equal to n. Why? So the number of elements are basically 9, so we'll initially update the lower bound to 10. Why we are doing this? Because in case if the element is not present, then we are planning to update the lower bound and upper bound as 10 initially. So we are initializing the values with size of the array initially. Okay, so that if the elements are not present, then the lower bound is basically equal to n initially. Now what will happen here is, firstly we will update the low index. So low will be initially at 0 and high will be standing where? High will be standing at 9. Now we calculate the mid. Now what is the midpoint? If you calculate the midpoint, right now it will come out as basically 4. So which element is there at the index 4? Notice that. So the element at the index 4 is basically the target element, which is nothing but 2 here. So we have found out the target element at this index. Now since we have found out the target element at this index, so we'll update the lower bound to this index, that is the mid index, which will be basically 4. So the lower bound will be updated to 4. But should we be satisfied? No, we do not want to find the index at which the target is occurring. We want to find the very first index at which the target is occurring. That is what is the definition of lower bound tells us about. So we want to find the very first index at which the target element is appearing. So that is why we will say that, okay, if the target element is present at this index, as of now we have stored this as the lower bound, as of now we have stored this as the answer, but we need to search for better. We need to search for lower index, because we want to find the lowest index or the smallest index at which this target element is appearing. So we need to search on the left side. So we will do what? We'll update the high to low like mid minus 1. So the high will get updated to what now? It will get updated to 3 here, because we need to search. Since we have found out the element here, we'll try to search on the left side of this element such that we can find the very first occurrence of 2 if it is appearing there also. Now what will happen here is, in this particular case, after this the midpoint will come out as what? After this, if you will calculate the midpoint will basically come out as nothing but 1 here, because if you see 0 plus 3 divided by 2 will come out as 1. Now the element that you are at is basically this index. Okay, so the element that you are at is still 2. The element is 2, but the index is 1 here. Okay, now does it equal to the target? Yes, it does equal to the target. So I'll update the lower bound to this particular index, that is 1 here. Now my lower bound is standing at 1. So after this, as I said, since I have found out the target element here, I'll try to search on the left side. So what will happen is my low, my high will be equal to mid minus 1, because if I have found out the target element here, I'll try to search on the left side of this mid, because I want to still find the very first occurrence of the target element. So now my high will be equal to what? It will be equal to mid minus 1. So it will be basically equal to what? 0 here, because mid is 1, mid minus 1 would be 0. Now if I'll calculate the mid, so mid will come out as 0, because 0 plus 0 divided by 2 is 0 itself. So we'll have 0. Now if I check the mid element at the mid index, so it is basically 1. Now it's not equal to the no, it is not equal to the target. Since it is not equal to the target, so we'll try to search on the right side. Okay, because if element at the mid index is not equal to the target, it is lesser than the target. So this means that we need to search on the right side of mid. So we'll update the low to what? Mid plus 1. When you update the low to mid plus 1, what happens? The low gets updated to basically index 1 here, and then you can see that the low and the high, they have crossed each other. So since they have crossed each other, so we need to stop at this point, and the lower bound has been found out as 1, because the lowest index at which the target element is occurring is basically 2 here. Now you need to make sure of one more thing, because you can observe that what is the definition of lower bound? The lower bound definition says that it will find the very first index at which the element is present, or it will tell us about the index where the target element needs to be inserted, because sometimes the target might not be present. So that is why what we will do is, while writing the code, we'll write this condition that if the element at the mid index, if it is what? If it is greater than equal to the target, then we'll store this particular index here. So we'll update the lower bound to what? We'll update the lower bound to this mid, because if the element is even greater, then also we'll store it, because sometimes if the element is not present, then we want to find the very first element that is greater, because we want to find the index at which we can insert the element. So that is why we are checking for the greater condition as well. Okay, now after this, lower bound will be updated as mid, and then high will be updated as what? Mid minus 1. Otherwise, if the element is not present at the mid index and we need to search on the right side, so else we'll do what? We'll update the low to what? We'll update the low to basically mid plus 1. If the element is not present at the mid index, and the element at the mid index is basically lesser than the target, then we need to search on the right side of mid. So low will be equal to mid plus 1 here. And I've told you why we are using the greater than condition, because lower bound, not only it will find the very first occurrence, but if the element is not present, then we need to find the very first index at which we can insert this particular element. Now let's talk about the upper bound concept also. Now upper bound concept will be very simple, because we need to find what? We need to find the index of the very first element that is greater than the target element. Okay, so let's see the dry run for the upper bound as well. What will happen is, initially low will be 0, high will be equal to 9. When we'll calculate the mid will come out as basically 4. Now let's update the upper bound variable here. So let's say we have the upper bound variable present here, and initially we'll update it to the size of the array here. So this will be basically 10 here. Now what will happen is, the mid is basically 4. So we are at this particular index. Now upper bound is what? Upper bound is the index of the very first element that is greater than the target. So is this particular element greater than the target? No, it is not. So we need to search on the right side. So we'll update the low to mid plus 1. So low will be equal to 5 now. After this, when we'll find out the midpoint, what will we get? The midpoint will be 5 plus 9 divided by 2. It will come out as 7. So now my mid is standing here. Now, is this particular element greater than my target element? Yes, it is. So I'll update the index here. So the index is basically 7. Element also is 7 here accidentally. So I'll update this particular index here, because this element is greater than the target. But I want to find the very first element that is greater than the target. So I need to search on the left side. If I find an element which is greater than the target element at the mid index, then I'll do what? I'll try to store that index, and I'll try to search on the left side, because I want to find the very first element that is greater than the target. So that is why we'll search on the left side. So we'll update the high as mid minus 1. So what will happen now is, high will be equal to 6 here. Okay, at this point, what will be my mid? Now my mid will be equal to basically 5 here. Now we check at the index 5, is the element greater than the target? Yes, it is. So we'll update the upper bound to this value 5 here, because the index 5 is having element 3, which is greater than the target. And I've told you that we'll try to find the very first occurrence of the element which is greater than the target. So that's why we'll try to search. If we have found out the element greater than the target at this mid index, we'll try to search on the left side, because we want to find the very first occurrence of the index that is greater than the very first occurrence of the element that is greater than the target. So we'll try to search on the left side. Now what will happen is, my high will be equal to mid minus 1. So high will be updated to 4. At this point, you see that low and high have crossed. So we stop here, and the upper bound stored is 5. So now if you'll observe, so for this particular question, my lower bound was updated as what? My lower bound was updated as 1, as index 1, and my upper bound was updated as what? As index 5. So you can see that the very first index at which my target element was appearing is 1, and the index that is the very first index that is greater than the target element is basically the index 5. So I have to do what? I have to subtract the upper bound index minus the lower bound index. That is the index of the element just greater than the target minus the index of the very first appearance of the target element. So when I'll do this, what will I get? 5 minus 1. This gives me 4. So it tells us that the target element here is present 4 times. Correct? So you can see here that the target element is basically present 4 times here. That's how we get this. Okay, I hope you have understood the dry run properly. Let's have a look at the code for the upper and the lower bound as well. Okay, so if you will see here, initially we have updated the result variable to the length of the array here. That is, initially we have updated the result to n here in lower bound function. Then we have the low and the high. Initially low is at 0, high is standing at the last index of the array, that is n minus 1. We'll iterate until the low is less than equal to the high. And what we will do is, we'll say that we'll calculate the midpoint, and if the element at the mid index is greater or equal to the target. Why we are checking for greater also? Because sometimes if the target element is not present, then we want to find the very first index at which we can insert the element. So we'll update the result to this mid, and then after that we will do what? We'll try to search on the left side, because we'll try to find the very first occurrence. If at this mid index I'm able to find the element, target element, still I'll try to find the very first occurrence of the index at which the target is appearing. So that is why we'll try to search on the left side of this mid. Otherwise, if at this mid index the element is not present, so this means that the element at this mid index is lesser. So we need to search on the right side. So So we'll do what? We'll do low is equal to mid plus 1, and at the end we'll return the lower bound index here, that is the index of the first occurrence of the target element. Okay, after this, talking about the upper bound function, we'll update the result is equal to the length of the array, and we'll have what? We'll have the low equal to 0, high equal to the n minus 1 index, that is the last index of the array. Then after this, upper bound is very simple, low is less than equal to high, and we want to find the index of the very first element that is greater than the target. So if the element at this mid index, if it is greater than the target, then we'll update the result to this mid. Okay, because if I find that at this particular index, this mid index, I have the element greater than the target, I want to store this, but I want to still find the very first index that is greater than the that is having element greater than the target. So I'll search on the left side of mid. So my high will be equal to mid minus 1. Otherwise, if at this mid index the element is lesser, so I'll search on the right side. So I'll update the low to what? Mid plus 1 here. And at the end, what we are going to do is we are going to return the result here, that is the upper bound. And after this, once we get the upper bound and the lower bound, we can simply do what? We can simply subtract upper bound value minus the lower bound value for this particular array here. Now let's try and code this up as well. So I've written the code here. You can see that the only change that I have done is that after applying the upper bound and lower bound function, I'm subtracting the values here. So let's submit this quickly and see if it is getting accepted or not. It should get accepted, hopefully. So you can clearly see that the code is getting accepted. I hope that you have understood this clearly. If you did, make sure to mention in the comments. Thank you for watching this video.